Be the last video that I'm going to make about diodes. So we're at part 7.7. Just to do a very quick recap. So far, what I've talked to you about diodes is the structure. So I've talked to you about the structure of a diode. I've talked to you about the characteristics of a diode. And when I was talking to you about the characteristics of a diode, I taught you three models that we use, right? The three models are the ideal, practical, and the simplified. But of course, usually what we do is that we use the simplified model, okay? The next thing is after we learned about what a diode is, I taught you how to use a diode. So the use was as a rectifier. It changes AC to DC. And there were two ways to do this, a half wave rectifier and a full wave rectifier. So this is one usage. Another usage was as a LED, right? Depending on the structure and depending on the materials used on the diode, is able to give off some light. And after that, what happens when we put 7 LEDs together? We get a 7-segment display. And then there were two kinds of 7-segment display, the common anode and the common cathode. Common cathode, right? So these are all the uses that these are all the points that I've talked about so far. Anytime you're not sure about what I'm talking about, please go back to the video, replay it. So for the last part of diodes, I'm going to introduce something to you called a Zener diode. So a Zener diode is something a little bit different from the normal diodes we've been talking about. Okay. Now, the weird thing about a Zener diode is that, okay, so basically what I've been telling you about is that you should not operate your basic diode in the breakdown region, right? You're going to damage your diode. But the funny thing about the Zener diode is that we do want to operate it in the breakdown region, okay? So the normal diode, we avoid driving it into breakdown region, but for the Zener diode, it is designed to work in the breakdown region. So we want to work it in the breakdown region. I'll explain to you how it works. Now, a Zener diode has what we call IZ, okay, the current running through the Zener diode. So what I taught you in the previous subchapters was we have a current running through from the anode to the cathode. Yeah. For a Zener diode, the opposite holds true. It's from the cathode to the uh, anode, and you can write that as it being such. IZ equals to the negative of ID. Negative being is in an opposite direction. Okay. Now, take note that this IZ only happens in the breakdown region. I'll explain to you later what it means. So this is the IV characteristic graph of a Zener diode. Okay, so take note, when it is forward bias, did I teach you about the symbol? This is the symbol. It's a normal uh, diode looking fella, except that it's got this little hook there. Okay, so when I have a Zener diode, when it is forward bias, it operates like a normal diode. So actually you can use a Zener diode as a normal diode. But what would be the point of that? If it's specially constructed to work in a breakdown region, let's take a look at how it works in a breakdown region. Okay. Now, so when the magnitude, when I reverse bias it, and the potential difference across it, the voltage across it, is greater than this fella here, VZ. And what is VZ? It is called the Zener voltage, VZ. When the applied voltage across the reverse bias Zener diode is greater than Vz, what happens is that you'll notice here the voltage stays constant at Vz. So the voltage doesn't um, increase. Okay, it sticks at Vz. It's a very sticky voltage here, Vz. So based on this, there are a couple of things that I can do with it. Yeah. Oh, sorry. Take note. If it's anything lower than Vz here, it's not really what we want. Yeah. We want to apply a voltage that is greater than Vz. And when we do that, the weird thing is that it doesn't actually go greater than Vz, it actually sticks at Vz due to this IV characteristic graph. So what we can do is we can regulate voltage. If over here you tell me that the voltage doesn't move, okay, it stays there. Well, if that's the case, there are certain applications, there are certain situations where we want the voltage to be constant. Yeah, so if we want something here, the voltage here to be constant, I can put a Zener diode here. Okay, so one application of a Zener diode is voltage regulation. Okay, so usually it consists of a resistor and a Zener diode over here. And remember, the Zener diode must be reverse biased. This is very important. So this will work so long as the value E is higher than Vz. Remember, here we want the voltage to be greater than Vz. Anything lower than Vz doesn't really work. We don't want to operate here. We want to get the voltage greater than Vz so that the voltage sticks here. Okay, so if I know that the voltage across here is going to be kept at a constant voltage, what I can do is that I can put a load across it so that this voltage, this Vz, is also, since these two are in parallel, is also applied here so that the voltage across the load will be the same voltage as the Zener voltage. Remember, voltage across parallel loads, voltage V1 and V2 are the same. Okay, so this is your basic DC circuits analysis. Right, so, but it's not as simple as that. We have to analyze it. One more time, I'll bring you back to this graph. Remember, we do not want anything lower than Vz. We do not want to be operating in this region. Okay, so we got to make sure that the voltage applied across it is not here. So let's do an analysis here, yeah? Okay, so if the voltage is lower than Vz, this fella acts as a open circuit. But to analyze it, we treat it as an open circuit first. Okay, so what we're going to do is that we're going to do a voltage divider. We are going to find what is the voltage here first. If the voltage here is lower than Vz, if the voltage here is lower than Vz, then it's not going to do anything. Okay, but if the voltage here is greater than Vz, if what you apply here is greater than Vz, and then this is where we are in the money, we are good. Okay, so let's use some numbers to talk about this. So this example has EMF 9 volts. I've got a resistor here. Remember, you always use it in tandem, in series with a resistor. So I've got my Zener diode, reverse bias. I've got my resistor 470 and my load 400. So remember, the first step is we treat the Zener diode as a open circuit. So using your voltage divider, okay, 400 over 470 plus 400 multiplied by 9, I get 4.1 volts. So I know that the voltage across my load is 4.1 volts. Now, the Zener voltage is 5.1. So what this means is that if I'm going to draw my IV characteristics of a Zener diode, we are not so concerned here because this is forward bias. We are concerned here, the reverse bias. They are saying that the Zener voltage is 5.1 volts. But here we are only having 4.1. So it's somewhere here, which is not what we want. We don't want this. We want it greater than 5.1. Remember, we want it greater than 5.1. Okay, so in this case, when it's lower than 4.1, the Zener diode acts as just like an open circuit. Yeah, so nothing happens here. The Zener diode is placed there basically for nothing. Waste of space, waste of resources. So to ensure that we properly make use of the Zener diode, let's increase the resistance of our load. So in this case, they're going to change the load to 1000 and we are going to do the same circuit analysis. Treat this fella as a open circuit, do a voltage divider. This time R is 1000. And I find that the voltage drop across here is actually 6.1 volts. 6.1 volts. Now, let's draw the IV characteristic graph again. IV, let's go back to maybe green this time. Same thing, I'm not too particular about what's happening here when it's forward bias because it is reverse bias. So I look here. The Zener voltage is 5.1, yeah? So now we are good because the voltage across it is 6.1 volts. So it's 6.1 volts, but it doesn't get to 6.1. It doesn't get here because the voltage is held at 5.1. Okay, it's stuck here, 5.1. So that's why the voltage across the load is kept at 5.1, even though our circuit analysis says that it is 6.1. Okay? So no matter what happens, no matter what you do, the voltage across here is always 5.1. So we are ensured we have a constant voltage of 5.1 volts. So it's a pretty useful thing, eh? The Zener diode. Okay, so if this is 5.1, I know that V1 is 9 minus 5.1. Okay, so this is 3.9 volts. Now bear with me, why am I doing this? Because if, let's kind of do a complete circuit analysis here, yeah? So if this is 3.9, I can actually find out what is the current going in here. Using Ohm's law, I'm over here, 3.9 over 470, I get 8.3 milliamps. Okay, and then applying Ohm's law here, remember it's 5.1, not 6.1. 5.1 over 1000, I get 5.1 milliamps. So this fella is 5.1 milliamps. So now applying Kirchhoff's current law, if the current coming into this node is 8.3, these two must equals 8.3. So if the 1 IL is 5.1, IZ must be 8.3 minus 5.1, I get 3.2 milliamps here. Okay, so for completeness sake, this is our complete circuit analysis for a Zener diode holding a constant voltage at the load. All right,